Hello, and welcome back to the MCAT grind. We have Organic Chemistry Chapter 2, Isomers. So, isomers, as you may know from the general chemistry, are two compounds that share the same chemical formula, but they may differ slightly to each other. When we're talking about OChem isomers, we have structural isomers, stereoisomers, conformational, and all the different types. So, to go through them, we have a flowchart. Here we have C6H14, so hexane. Now, we also have a 6 carbon chain, but it is differed in structure. We call this structural isomers to each other because the bond is connected differently. So, they don't have the same connectivity, then they're structural isomers. If their connectivity is the same, then they're called stereoisomers. Stereoisomers, if they don't have a bond break in between them, then they're conformational. Think about if this is a single bond. The two constituents here, they could rotate around and still be the same from each other. So this formation is the same as this formation, but only differs in the rotation here. The problem is, with this formation, you could get certain strains that make it unfavorable. This isomer is more unfavorable if it's like this. How so? Well, there are angle strains, which means that from the ideal angle of 120 degrees apart, if the angle gets pressed together like this by some reason, then these compounds will exert force on each other and that make it unfavorable and higher energy state. Remember, lower energy state is better, or compounds prefer that way. Torsional strain is when compounds are around a bond and you go from a lower energy state to a higher energy state by forcing that pull. Think about a rubber band and you start twisting it. You make a tension in that string and torsional strain. And when you let go, it will come back to a normal state. So we have two main states. One is called eclipsed, where they are overlapping each other, and another is called staggered, where you can see that they're staggered in formation with each other. This is a Newman's projection, meaning the ones at the front are showing towards us and the ones in the back are away from us. You can see there's a circle. The ones that join in front of the circle is towards us, and one coming out from the back of the circle is in the back. The last strain is non-bonded strain. Non-bonded strain happens when you have a cyclic compound and you have axial versus equatorial. This may also happen not in cyclic compounds, but if we have a compound like so, there may be other constituents at the tip here. For example, ethylene, ethene coming out from here, and maybe carboxyl group coming out from here. Those groups may propel each other because they're competing for the same space here. Electron cloud space here that they may push each other away a bit further, so you may not have a perfect staggered position. It may be even further. So non-bonded strains are mostly caused by van der Waals forces. Now, jumping into configurational isomers, there is a bond break between the two isomers. From conformational isomers, we can just twist them into one another. Configurational, there is a bond break to make them not be able to get to each other from just twisting the bonds. Think about your hands. In mirror images, your right hand is a mirror image to your left hand. You have a mirror here. Boom. That is a mirror. Now, mirror images cannot superimpose on another. See, my right thumb will always go to this way, but my left thumb always goes to the other way. So I cannot put them over on top of each other and they're not identical. Those are enantiomers. Diastereomers, however, are not mirror images to each other. So think about my right hand, left hand. If I'm carrying, if my right hand instead has a finger going down this way, my left hand can't replicate that in a mirror image, right? And additional from that, if there's an immovable bond in between, like this, I can't twist this over and cross because it's not a single bond, then that means it is cis-trans isomers to each other. Cis means same side, so it's denoted by Z. Z, you can think of it as same side, and trans, you can say it as opposite side for E. So if I have my big functional group for my fingertips and they're pointing to the same side, that's cis isomer. If they're opposite from each other, then they're trans isomers. Alright, then we have what the R and S denotes is a Kant-Ingold naming system. So, if I have an isomer, think about, I like to use my hand, you first label the functional groups. You always label the functional group or the connected atom with the highest atomic number as possible and label that as 1. Then you go by order, and 4 should always be the lowest one, which is hydrogen usually. What you would do then is put hydrogen at the bottom, and let's say my index is bromine, my middle finger is chlorine, and my thumb is helium. It's a random example, but bromine is highest, is like 35, and my middle finger would be chlorine. I don't know, that's 17 maybe, and helium is 2. So this would be the highest. So 1, 2, 3, and 4 will be my hydrogen. So I would go around this like a top, around this way, and that is clockwise. So that would be the R configuration for this chiral center of carbon. Remember, carbon is in the center. Okay. Now, if it's going the other way, bromine, chlorine, and a helium, then the order would go like this. Remember, hydrogen is at the bottom because it's a number 4. When it goes like this, it would mean S. The S configuration for this chiral compound, because it goes counterclockwise. Next, we have specific rotation. Specific rotation is the way the molecule starts to rotate on itself when it's exposed to polarized light. When polarized light hit the compound, it will either spin dextrorotatory, which means clockwise, or spin lever rotatory, or spin counterclockwise. It cannot be determined from looking at the structure itself, only conducted experimentally. You can achieve and obtain that specific rotation by noting down the observed rotation and dividing that by the concentration in grams per milliliter, or pretty much the concentration itself. And this is key point, in decimeters. Many questions give you in centimeters, so you really have to multiply that by 10 to get the decimeters. That's where many makes the mistake. Then we have different forms for cyclic compounds. Puckered is for 1, 2, 3, 4 compounds in the cyclic butane. Envelope form is the most energy favorable for cyclic pentane. Chair formation is 1, 2, 3, 4, 5, 6 is the most energetic favorable for cyclohexane. Cyclohexane also has boat and twist boat formations, but those are less energy favorable. The chair formation has the constituents most far away from each other and the most thermodynamically stable of all. Now, you can convert interchange to different formations, but you will need to add energy into the system. Alright, that's pretty much it for isomers. Good luck for the grind.